Imagine standing beneath a clear night sky, looking up at the stars. The universe stretches endlessly, and the light that reaches your eyes may have traveled millions of years just to meet you. On the surface, it feels simple. Light shining, your eyes receiving, your brain understanding. But hidden beneath that simplicity is a world so strange, so different from our everyday experience, that it challenges the very way we think reality works. This hidden world is the world of quantum physics. Quantum physics is not just another branch of science. It's a doorway into the invisible mechanics of the universe. It explains why the sun shines, why atoms hold together, and even why you are here to ask these questions. But the road to understanding it is not straightforward. It demands that we let go of everyday intuition, because the rules that govern the tiniest building blocks of reality are unlike anything we encounter in daily life. Here, particles can be waves, certainty dissolves into probabilities, and observation itself shapes the outcome of events. It sounds like science fiction, yet it is the most tested and successful framework in all of physics. Before diving into these mind-bending ideas, it's worth asking a simple question. Why do we even need quantum physics? For centuries, classical physics, built on the ideas of Isaac Newton, seemed to explain the world beautifully. Objects moved when pushed, planets orbited under pull of gravity, and light seemed to behave like waves traveling through space. For most of human history, that picture was enough. But cracks began to appear at the turn of the 20th century. Light sometimes behaved like particles. Energy didn't flow continuously, and atoms, supposedly the indivisible building blocks, contained mysteries that classical physics couldn't unravel. These cracks didn't mean physics was broken. They meant something deeper was waiting to be discovered. To start slowly, let's think about the concept of energy. In classical terms, energy can take many forms. The motion of a rolling ball, the warmth of the sun, or the vibration of a string. It was assumed energy could vary smoothly, like water flowing in a river. But experiments revealed something startling. When scientists studied how heated objects glowed, they found energy didn't behave as a smooth flow. Instead, it came in tiny, discrete packets, like drops of water rather than a continuous stream. This was the first glimpse into the quantum world. Energy was quantized. That discovery alone was revolutionary. It suggested that the universe, at its most fundamental level, operates in steps rather than smooth curves. The term quantum itself simply means packet or discrete amount. Imagine dimming a light in your room. Classical physics would predict you could reduce its brightness smoothly, with no limit. But quantum physics says there's a smallest possible unit of light, called a photon. You can't divide it further. It is the atom of light itself. This realization set the stage for an entirely new way of thinking. Now, if light could be particle-like, then what about matter? That question led to the idea that electrons, protons, and neutrons, the stuff that makes up atoms, also had wave-like properties. The deeper scientists looked, the more they realized the boundary between particles and waves was not a boundary at all. Instead, reality seemed to blend the two into one strange duality. A particle was not just a point, and a wave was not just a ripple. Things could be both at once, depending on how you looked at them. This was shocking, because it violated common sense. Yet experiments confirmed it again and again. The most famous experiment to reveal this was the double-slit experiment. Imagine shooting tiny particles, like electrons, through two narrow slits at a screen. If they behave like tiny bullets, you'd expect to see two clusters where they hit. But instead, they create a pattern of stripes, as though they were waves interfering with each other. Even stranger, if you try to observe which slit the particle goes through, the interference pattern vanishes, and the particles behave like bullets again. It is as if the universe waits to see whether you are looking and only then decides what to do. Reality at the quantum level is not fixed, but fluid, sensitive to the act of measurement. This leads us to one of the most important principles in quantum physics: uncertainty. In our everyday world, if you know where a ball is and how fast it's moving, you can predict where it will be in the future. That's the essence of Newtonian physics. But at the quantum level, Heisenberg's uncertainty principle tells us you can't know both position and momentum of a particle with perfect accuracy. The more precisely you try to pin down one, the fuzzier the other becomes. It's not a flaw in measurement tools. It's the way nature works. At the heart of reality lies uncertainty. Now, you might wonder, how could a universe built on uncertainty ever give rise to the stable, predictable world we see around us? How can tables, trees, and stars exist if their foundations are governed by probability? The answer lies in scale. Quantum effects dominate the microscopic world of atoms and particles, but as countless of them come together, their collective behavior smooths out into the apparent solidity of the macroscopic world. Still, without those quantum rules, atoms wouldn't form, chemistry wouldn't exist, and life as we know it would be impossible. At this point, it's natural to feel a bit disoriented. A universe that changes when observed, a world where energy comes in steps and particles are also waves. But remember, the goal here is not to swallow it all at once. It's to move slowly, step by step, and let these ideas sink in. Quantum physics asks us to let go of rigid certainty and embrace a new kind of understanding, one that accepts probabilities, dualities, and mysteries as part of the very fabric of existence. What's most astonishing is that this strange, counterintuitive theory is not just philosophy. It powers real technologies we use every day. Without quantum physics, there would be no lasers, no smartphones, no computers as we know them, and no medical imaging techniques. The very chips that process information in your devices rely on the quantum behavior of electrons moving through materials. Far from being abstract, quantum physics is woven into the fabric of modern life. And yet, despite its success, it raises profound questions about the nature of reality. Are particles real before we measure them? Does the act of observation create outcomes? What lies beneath the probabilities that quantum mechanics so precisely describes? These are questions that physicists, philosophers, and thinkers still grapple with today. But for now, the important step is simply to recognize that the quantum world is different. Strange, yes, but also deeply beautiful in its strangeness. So as we begin this journey, keep in mind, we are stepping into a realm where the rules bend, where certainty gives way to possibility, and where our everyday logic must be set aside. The world of the quantum is not just about equations or experiments. It's about rethinking what it means to understand the universe. And we will take this journey slowly, carefully, one step at a time. Because only by moving slowly can we begin to glimpse the vast and wondrous truth hidden beneath the surface of reality. In our first step, we open the door to quantum world, a place where certainty fades and probability reigns, where light behaves as both a particle and a wave, and where the act of observation shapes reality. It was a glimpse into a landscape that feels unlike anything in our daily lives. But to truly appreciate this world, we need to go deeper into its key principles and understand how scientists discovered them in the first place. Because quantum physics isn't a random collection of odd facts. It is a carefully built structure shaped by evidence, experiment, and relentless curiosity. Let's start with something deceptively simple: the atom. For centuries, the atom was imagined as the indivisible unit of matter, a tiny solid sphere. But discoveries in the late 19th and early 20th centuries shattered that picture. Atoms turned out to have structure, a dense nucleus at the center made of protons and neutrons surrounded by electrons. But here's the puzzle. According to classical physics, electrons should spiral into the nucleus. Moving charges radiate energy, and so electrons should lose energy, collapse inward, and the atom should not even exist. Yet atoms clearly do exist, and they are stable. Something was wrong with the old picture. The solution came from the realization that electrons don't orbit like planets. Instead, they exist in discrete energy levels or shells around the nucleus. An electron cannot exist between these levels. It can only jump from one level to another, absorbing or releasing energy in the form of photons. This leap is not smooth. It's instantaneous, as though the electron simply vanishes from one orbit and appears in another. This is called a quantum jump. Strange as it sounds, it explained why atoms are stable. Electrons are not allowed to collapse inward unless energy rules permit them to. These jumps also explain why heated gases or glowing stars emit light in specific colors. Each element has its own pattern of energy levels, and when electrons leap between them, they release photons of particular wavelengths. When scientists passed this light through a prism, they saw not a continuous rainbow, but distinct lines, fingerprint of the atoms. These spectral lines were the proof that energy in atoms comes in quantized steps, and they became one of the cornerstones of quantum theory. This picture of electrons also led to the understanding of why matter has structure at all. Without quantization, electrons would fall into the nucleus, and atoms would collapse. But because they can only occupy specific states, matter becomes stable, and complex structures like molecules, cells, and eventually people are possible. In a very real sense, the rules of quantum physics are the reason the universe is not just an empty void. But let's not rush. If electrons exist in specific states, what does that mean for their exact position? This is where the quantum story gets even stranger. Instead of being tiny balls orbiting neatly around the nucleus, electrons behave more like clouds of probability. They don't have a single definite location until we measure them. Instead, they exist in what is called a wave function, a mathematical description that tells us the likelihood of finding the electron in a particular place. When we make a measurement, the wave function collapses, and we detect the electron at a specific spot. Until then, it is not in one place, but many places at once, spread out like a mist. Think of it like this. Imagine a spinning coin in the air. While spinning, it's neither heads nor tails. It's in a blur of both. Only when it lands, and you look at it, does it become one or the other. The electron situation is similar, but even more profound. It's not just that we don't know where it is. It's that, according to the quantum description, it genuinely does not have a definite position until it interacts with the world in some measurable way. This brings us to the heart of quantum weirdness: superposition. A particle can exist in multiple states simultaneously. An electron can be here and there, spin up and spin down, until observation forces a choice. This isn't just a theoretical idea. It's been demonstrated countless times in experiments. And it leads us to one of the most famous thought experiments in physics: Schrödinger's cat. Imagine a sealed box containing a cat, a vial of poison, and a radioactive atom. If the atom decays, the vial breaks, and the cat dies. If not, the cat lives. According to quantum rules, until the atom is observed, it is in a superposition of decayed and not decayed. That means the cat is both alive and dead, at least in the mathematical description, until the box is opened. It sounds absurd, and it is. Schrödinger himself proposed it not to suggest cats can be both alive and dead, but to show how bizarre quantum principles seem when extended to the everyday world. Still, the experiment captures the essence of quantum superposition. Things can exist in multiple possibilities at once, only becoming definite when observed. But what does observation mean in this context? This is one of the deepest puzzles in physics. Does it require a conscious observer? Or is it enough that a measuring device interacts with the system? Different interpretations of quantum mechanics offer different answers. Some say the universe splits into multiple versions at each observation, each outcome playing out in a different branch of reality. Others say the wave function reflects our knowledge, not the particle's reality. The truth is, no single interpretation has been universally accepted. What all physicists agree on is the mathematics. The predictions work, and the experiments confirm them. Beyond that, the meaning is still an open debate. Let's pause here to reflect. Atoms are stable because electrons exist in quantized states. Light comes in packets called photons. Particles like electrons exist not as tiny balls, but as wave-like clouds of probability. And reality itself is not fixed until observed. These are not just ideas. They are experimentally verified facts. Quantum mechanics is not just a theory in the abstract sense. It's the most precise scientific framework we have, with predictions confirmed to astonishing accuracy. Yet, for all its success, it doesn't give us the kind of certainty we might crave. It gives us probabilities, possibilities, and mysteries. And that's perhaps the most important lesson to absorb at this stage. The universe, at its foundation, is not a clockwork machine grinding away with perfect predictability. It is a dance of probabilities, a play of possibilities, and we are participants simply by being observers. This shift in perspective has profound consequences. It challenges the idea that the world is entirely objective and independent of us. It suggests that our interaction with reality is woven into its very fabric. It also reminds us that knowledge is not always about certainty, but about understanding the range of what is possible. In the quantum world, possibility is not weakness. It is a very structured reality. As we continue, we'll explore how these principles aren't just philosophical curiosities, but practical foundations for modern technology. Superposition, uncertainty, and quantization power the computers, lasers, and electronics we depend on every day. They also open the door to new frontiers, like quantum computing and teleportation. But before we get there, we need to make sure the core principles are firmly understood. Because in quantum physics, each step builds on the last, and moving slowly is a key to truly seeing the picture. So far, we've seen that quantum physics reshapes how we think about light, atoms, and measurement. In the next stage, we'll peel back more layers, looking at the strange behavior of particles, the importance of entanglement, and the way information itself becomes part of the story. For now, hold on to this foundation. The world at its core is quantized, uncertain, and astonishingly alive with possibility. That is the essence of the quantum revolution. We've now walked through the basics of quantization, superposition, and uncertainty. These principles already feel strange enough, but they are only the beginning. The deeper we go, the more the quantum world bends our everyday logic. At this stage, we're ready to meet one of the most mysterious and fascinating features of quantum physics: entanglement. This phenomenon has been called spooky action at a distance, and for good reason. It suggests that particles, once linked, remain connected no matter how far apart they are, as if the universe itself refuses to separate them. To understand this, we need to slow down and build carefully. Let's begin with a simple picture. Imagine two particles created together in such a way that their properties are linked. For instance, think of their spins, tiny quantum versions of rotation. If one particle is spin up, the other will always be spin down. The exact orientation doesn't matter. What matters is that the two are opposite. Now, here's the twist. Until we measure one of them, neither has a definite state. They are in a superposition of both up and down. But the instant we measure one particle and find, say, spin up, the other particle instantly becomes spin down, no matter if it's sitting beside us or light years away. This is entanglement. To see why this is strange, remember that quantum particles don't carry hidden instructions with them. They are not secretly deciding in advance what outcome they'll show. Experiments have ruled that out. Instead, the act of measuring one particle somehow determines the state of the other instantly. It's as if the two particles are part of one single system, even when separated by immense distances. Einstein famously disliked this idea. He called it spooky action at a distance, and argued that quantum mechanics must be incomplete. He believed there had to be some hidden variables, unknown properties, that explained the correlation. But decades of careful experiments have shown otherwise. Quantum mechanics was right. Entanglement is real. At first glance, this seems to break one of the fundamental rules of physics, that nothing can travel faster than light. If measuring one particle instantly affects the other, doesn't that mean information is traveling faster than light? The answer is subtle. Entanglement does not allow us to send messages or signals faster than light. What it does reveal is that the particles are not separate in the way we think. They are part of a shared quantum state, and the universe treats them as one system, no matter the distance. In other words, the strangeness is not about faster-than-light communication, but about the very definition of separateness. So what does entanglement mean for our understanding of reality? It means that the universe is more interconnected than classical physics ever allowed. It suggests that the world cannot always be broken down into independent parts. Instead, parts of the universe can remain fundamentally linked, sharing properties in a way that defies everyday logic. This realization is more than a curiosity. It's one of the deepest insights we have about the nature of reality. It tells us that wholeness and connection are baked into the very fabric of existence. Let's make this more tangible. Suppose you had two dice that were quantum entangled. Normally, if you roll two dice, the results would be independent. But with entangled dice, if one landed on 3, the other might instantly land on 4, perfectly correlated every time. You wouldn't know what either die would land on until you looked. But once you did, the result of one would determine the other. That's what happens with quantum particles. It's not about cheating or hidden gears inside the dice. It's about a deeper rule of reality that classical logic cannot capture. This raises profound philosophical questions. If entangled particles behave as one system, then what does that say about the universe itself? Are we all entangled in some vast cosmic web? Some interpretations suggest that entanglement is not an exception but the rule, that the universe is fundamentally holistic, with separateness being only an illusion. While such ideas are speculative, they capture the spirit of what quantum physics invites us to consider. That reality is stranger, more interconnected, and perhaps more unified than we ever imagined. But entanglement is not just a philosophical puzzle. It has real practical applications. In recent years, scientists have learned to harness entanglement for new technologies. One of the most exciting is quantum communication. By entangling particles and sending them to different locations, information can be shared in a way that is incredibly secure. If anyone tries to tamper with the system, the entanglement breaks and intrusion is revealed. This has led to experiments in quantum cryptography, where messages can be transmitted with unprecedented safety. Governments and research labs are investing heavily in this, seeing it as the future of secure communication. Another application is quantum computing. Ordinary computers use bits, zeros, and ones as their basic units of information. But quantum computers use qubits, which can exist in superpositions of 0 and 1 at the same time. When qubits are entangled, their power grows exponentially, allowing quantum computers to tackle problems that classical computers could never handle. While still in its infancy, quantum computing promises to revolutionize fields from medicine to finance, offering new ways to simulate molecules, optimize systems, and even break current encryption methods. So entanglement, once dismissed as a bizarre quirk, is now at the heart of a technological revolution. It shows us that the strangeness of the quantum world is not a flaw but a resource, something we can harness to reshape our future. And it also reminds us of a deeper lesson, that our intuition, shaped by the macroscopic world, is not always the best guide. To truly see the universe, we must be willing to think differently, to let go of old assumptions and embrace the new. Now, let's tie this back to our larger story. We began with quantization, energy in discrete packets. We moved to superposition, particles existing in multiple states at once. We encountered uncertainty, the idea that reality is fundamentally indeterminate until measured. And now, with entanglement, we see that even distance and separateness are not as clear as we thought. Each step reveals another layer of strangeness, yet together they form a consistent, powerful picture. This is the essence of quantum physics, a world that seems paradoxical, yet works with unmatched precision. As we continue, the question becomes, what does all this mean for our place in the universe? Does entanglement hint at a deeper unity that connects us to the cosmos? Does uncertainty mean that free will is possible in a way classical physics never allowed? These are not just scientific questions, but human ones, because quantum physics forces us to reconsider the most basic assumptions about existence. It invites us to see reality not as a machine, but as a living, dynamic web of possibilities. In the next step, we'll look at how the strange rules of quantum physics have shaped our modern world. From the chips in our phones to the lasers in our supermarkets, quantum mechanics is everywhere, silently powering the technologies we take for granted. By seeing how theory became practice, we'll deepen our appreciation for how a once bizarre idea reshaped civilization. But for now, hold on to this. Entanglement shows us that the universe is not a collection of separate objects, but a deeply interconnected whole, where distance and separateness dissolve in the face of quantum truth. So far, we've taken a journey through the strange landscape of quantum physics. We've seen how energy comes in discrete packets, how particles can exist in multiple states at once, how uncertainty limits what we can know, and how entanglement links particles across space in mysterious ways. Each of these ideas on its own is strange enough, but together they form a new framework for understanding reality. The question now becomes, why should we care? Are these principles just abstract curiosities for scientists to debate, or do they truly matter to our everyday lives? The answer is clear: they matter enormously. In fact, quantum mechanics is the hidden engine behind much of modern technology. Without it, the world we live in would look entirely different. Let's begin with something we all rely on every single day: electronics. The tiny devices that power our lives, smartphones, computers, televisions, and more, depend on the quantum behaviors of electrons and materials. To understand this, let's step back for a moment and think about what makes materials conduct electricity. In classical physics, you might imagine electrons flowing through a metal wire like water through a hose. But the truth is far subtler. In metals, electrons are not bound tightly to atoms. They can move freely, forming a kind of electron sea. In insulators, on the other hand, electrons are locked in place, unable to move. The difference between these two behaviors, conductor and insulator, comes from quantum mechanics. Electrons exist in energy levels, and in solids, these levels form bands. When a band is full, electrons can't move freely, and the material behaves like an insulator. When bands overlap or have room for electrons to move, the material becomes a conductor. And in between, we have semiconductors, where electrons can be nudged into higher energy levels, allowing carefully controlled conductivity. This is the foundation of modern electronics. The transistors inside your computer or phone are tiny switches that control the flow of electrons, built on the quantum behavior of semiconductors. Without quantum mechanics, the entire digital revolution would never have happened. Next, consider light itself. We learned earlier that light comes in packets called photons. Harnessing this idea gave birth to one of the most important inventions of the 20th century, the laser. The word laser stands for light amplification by stimulated emission of radiation. It's a mouthful, but the idea is simple. By exciting atoms to higher energy states and then triggering them to release photons in a controlled way, we can produce a beam of light that is coherent, focused, and incredibly precise. Lasers are not science fiction. They are everywhere. In supermarket scanners, DVD players, medical surgeries, and even the fiber optic cables that carry the internet around the globe. Every time you stream a video or scan a barcode, you are using quantum physics in action. Medical imaging provides another example. Techniques like MRI, magnetic resonance imaging, depend on the quantum behavior of atomic nuclei in magnetic fields. By exploiting the way nuclear spins respond to carefully tuned magnetic pulses, doctors can create detailed images of the inside of the human body without surgery. Quantum rules, once thought abstract and bizarre, are now tools that save lives every day. Even something as simple as the sun shining in the sky is a quantum story. The sun's energy comes from nuclear fusion, the process of atoms merging under extreme pressure and temperature. For fusion to occur, protons must overcome their mutual electrical repulsion. Classically, this seems impossible to conditions inside the sun. The protons don't have enough energy to collide. But quantum mechanics provides the answer through a phenomenon called tunneling. Tunneling allows particles to pass through barriers that classical physics says they cannot. In the sun, this means protons can tunnel through their repulsion, allowing fusion to happen and sunlight to reach Earth. Every ray of sunlight warming your face is a gift of quantum tunneling. Quantum tunneling also powers modern electronics. In flash memory, the kind used in USB drives and solid-state devices, electrons tunnel through thin barriers to store information. Quantum mechanics is literally etched into the devices we use daily. The world we live in, digital, connected, and powered by tiny circuits, rests firmly on the shoulders of quantum principles. Now, let's think about the sheer accuracy of quantum mechanics. Some of its predictions have been tested to astonishing precision. One famous example is the magnetic moment of the electron, a tiny property related to its spin. Quantum electrodynamics, the branch of quantum theory dealing with particles and light, predicts its value with incredible accuracy. Experiments have measured it to more than 10 decimal places, and the theory and experiment match almost perfectly. This kind of agreement is unheard of in science. It tells us that quantum mechanics is not just a good idea. It is the most successful scientific theory humans have ever created. But as much as quantum mechanics underlies the technology around us, it also points to the future. Quantum computers, still in their early stages, promise to transform how we solve problems. By exploiting superposition and entanglement, quantum computers can perform calculations in parallel, exploring possibilities far faster than classical machines. Imagine simulating the behavior of complex molecules to design new medicines, optimizing logistics for entire cities, or cracking codes that are currently unbreakable. These are the promises of quantum computing. While challenges remain, the direction is clear. Quantum mechanics is not just a past and present technology, it is the future. Yet it's important to pause here and reflect. The technologies we've described, lasers, semiconductors, MRI, tunneling, quantum computing, are not the product of science fiction. They are the direct consequence of carefully studying the strange, counterintuitive rules of the quantum world. What once seemed bizarre or even absurd has become practical and indispensable. This is a powerful reminder of the value of curiosity. By daring to ask strange questions, why atoms don't collapse, why light comes in colors, why particles behave like waves, scientists unlock truths that transform the world. At this point, we should step back and recognize a larger theme. Quantum mechanics is not just about equations or gadgets. It is a story about human imagination. It is about our willingness to accept that the universe might not fit neatly into our everyday expectations. Instead of rejecting the strange, we explored it. Instead of clinging to certainty, we embraced probability. And by doing so, we open doors to new realms of knowledge and power. Still, quantum physics is not finished. The more we explore, the more questions arise. How do we reconcile quantum mechanics with gravity, the force that shapes planets and galaxies? Why does observation collapse the wave function? Is entanglement hinting at a deeper structure of reality that we have yet to uncover? These are questions at the frontier of science, waiting for answers. Quantum mechanics gives us incredible predictive power, but its deeper meaning is still shrouded in mystery. As we prepare to go further, keep this balance in mind. Quantum physics is both deeply practical and profoundly mysterious. It powers the devices in your pocket, yet also challenges the very nature of reality. It is at once the most useful tool we have and the most puzzling riddle we face. This dual nature, practical and mysterious, is what makes quantum physics so compelling. It reminds us that science is not just about utility, but about wonder, not just about answers, but about questions. In the next stage of our journey, we will turn from technology back to interpretation. We've seen what quantum mechanics does, but what does it mean? How should we understand a universe where particles can be waves, outcomes are uncertain, and entanglement binds distant things together? In Part 5, we'll explore the major interpretations of quantum mechanics, the different stories scientists tell to make sense of the mathematics. Some are realists, insisting the world exists independently of observation. Others are radical, suggesting reality itself is shaped by our interaction. Each offers a different lens through which to see the quantum world. And through these interpretations, we'll see how quantum physics challenges not only science but philosophy itself. Up to now, we have focused on the principles of quantum mechanics and the technologies they make possible. We've seen how quantization, superposition, uncertainty, and entanglement provide the foundation for everything from semiconductors to lasers, from medical imaging to the shining of the sun. The strange has become practical. But there's another side to this story, one that is not about gadgets or experiments, but about understanding. If quantum mechanics works so well, what does it tell us about reality itself? What does it mean that particles can be in two places at once, that observation shapes outcomes, or that entangled particles remain connected across space? These are the questions of interpretation. Unlike classical physics, where the rules were intuitive, objects of definite positions, causes lead to effects, quantum physics leaves room for ambiguity. The equations describe probabilities, not certainties. The wave function evolves smoothly, but then seems to collapse into definite outcomes when measured. What is really happening? Does the wave function represent reality, or just our knowledge of it? These questions have inspired multiple interpretations of quantum mechanics, each attempting to make sense of the same mathematical framework. None has been universally accepted, but each opens a different window into the nature of reality. Let's begin with the most traditional, known as the Copenhagen interpretation. Developed in the early 20th century, it suggests that the wave function does not represent physical reality, but rather our knowledge of a system. In this view, particles do not have definite properties until we measure them. The act of observation collapses the wave function into a single outcome, and before that collapse, asking about what really exists is meaningless. This interpretation is pragmatic. Don't ask what is happening behind the scenes. Just use the equations to predict outcomes. For many physicists, this shut up and calculate approach was enough. It allowed science to move forward without getting stuck in metaphysical debates. But not everyone was satisfied with this. Some felt the Copenhagen interpretation left too many questions unanswered. Was reality really dependent on observation? Did the universe exist in a fuzzy state until someone looked at it? This unease gave rise to alternative interpretations. One of the most famous is the many worlds interpretation. According to this view, the wave function never collapses. Instead, every possible outcome of a quantum event actually occurs, but in different branches of the universe. When you measure a particle that could be spin up or spin down, both outcomes happen, one in your universe and one in another equally real universe. In this way, reality constantly splits into countless versions, each carrying forward a different outcome. It's a bold idea, suggesting that the cosmos is an infinite multiverse of possibilities. The many worlds interpretation solves one puzzle. It removes the mysterious collapse of the wave function, but it raises another. If all outcomes occur, what does that mean for our sense of choice, our uniqueness, our experience of reality? Are there endless versions of us living out alternate lives in parallel universes? It is a staggering thought, and while many worlds is elegant in some respects, it is also unsettling. Another approach is the pilot wave theory, also called Bohmian mechanics. In this interpretation, particles always have definite positions, but they are guided by a hidden wave that determines their behavior. This wave evolves according to quantum rules, creating the strange patterns we see in experiments like the double slit. Unlike Copenhagen, this interpretation insists that reality is definite and objective. There is no collapse, no fuzziness, just particles and waves working together. The catch is that this guiding wave operates in a way that is non-local, meaning it connects distant particles instantly. This brings us back to that spooky action Einstein disliked, but it also restores a sense of reality that feels more solid. There are other interpretations too. The objective collapse theories suggest that wave function collapse is a real physical process, not just an update of knowledge. According to these ideas, quantum superpositions naturally collapse after a certain time or size, preventing the absurdity of things like Schrodinger's cat being alive and dead. Then there are relational interpretations, which suggest that reality is not absolute but depends on interactions. In this view, properties only exist in relation to other systems, never in isolation. Reality, then, is not a fixed stage but a network of relationships. The variety of interpretations highlights something important. Quantum mechanics is not just a scientific theory, but a philosophical challenge. The mathematics works flawlessly, but what it tells us about the nature of reality is still debated. Some physicists argue that interpretation doesn't matter, that as long as the predictions match experiments, we should leave the rest to philosophers. Others argue that understanding what quantum mechanics means is essential to truly grasping the universe. The debate continues, and it may never be settled. But why does this matter to us? Why should we care which interpretation is true? Because interpretations shape how we think about reality itself. If Copenhagen is right, then reality is fundamentally probabilistic, existing in a haze until observed. If many worlds is right, then every moment spawns infinite universes, and our reality is just one of countless branches. If pilot wave theory is right, then the universe is deterministic after all, with hidden order guiding everything. Each interpretation carries different implications for our understanding of existence, consciousness, and even free will. This brings us to one of the most intriguing questions. What role, if any, does consciousness play in quantum mechanics? Some interpretations suggest none at all. Measurement is simply any interaction that forces a choice. Others, more speculative, suggest consciousness itself might be entangled with the process, that the act of awareness somehow collapses possibilities into reality. While these ideas are controversial and often overstated, they remind us that quantum mechanics pushes us to the edge of what science and philosophy can explore together. At this point, it is worth pausing to reflect on the journey so far. We've moved from the practical, how quantum mechanics explains atoms and powers technology, to the philosophical, what quantum mechanics says about reality itself. This dual nature is what makes quantum physics so fascinating. It is both a tool and a mystery, both a practical guide and a profound riddle. And the fact that multiple interpretations can coexist shows that our journey is far from over. We understand the rules, but the story behind them is still unfolding. As we continue, we'll explore how quantum mechanics reshapes our understanding of space and time. We've seen how entanglement challenges separateness. But what happens when we bring relativity, the physics of the very large, into the picture? How do quantum mechanics and gravity fit together, if at all? This is one of the greatest challenges in modern science. And in our next step, we'll slowly begin to explore the search for unity, a quest to connect the quantum world of the very small with the cosmic world of the very large. The journey so far has revealed how quantum mechanics explains the invisible dance of particles, fuels our technologies, and challenges our understanding of reality itself. We've looked at different interpretations, whether reality splits into many worlds, whether it hides in guiding waves, or whether it flickers into being only when observed. Yet all of these discussions have lived firmly in the realm of the very small, atoms, electrons, photons. But our universe is not only microscopic. It is vast, filled with stars, galaxies, and black holes, where the laws of gravity dominate. This raises a profound question. How do the rules of the very small connect the rules of the very large? And can they be united into a single, consistent framework? To explore this, we need to recall another towering achievement of 20th century science, Einstein's theory of relativity. Relativity, unlike quantum mechanics, deals with the grand stage of space, time, and gravity. It tells us that time slows down near strong gravitational fields, that space itself can curve, and that matter and energy are two sides of the same coin. Its predictions have been confirmed again and again, from the bending of starlight by gravity to the precise ticking of satellites in orbit that make GPS possible. Relativity is elegant, continuous, and deterministic, a universe of smooth curves and predictable motion. Quantum mechanics, on the other hand, is discrete, uncertain, and probabilistic. It describes a universe where events jump rather than flow, where outcomes cannot be predicted with certainty, and where particles seem to exist in clouds of possibility until pinned down. In some sense, relativity and quantum mechanics speak entirely different languages. One deals in smooth geometry, the other in sharp probabilities. And yet both are true. Both work within their domains with astonishing accuracy. The challenge is that when we try to bring them together, say, in the heart of a black hole or in the very first moments of the Big Bang, they clash. To see the problem, imagine trying to describe a black hole. A black hole forms when a massive star collapses under its own gravity, compressing matter into a tiny point of infinite density, known as a singularity. According to relativity, space-time curves infinitely at that point, creating a region where even light cannot escape. But quantum mechanics refuses to accept infinite density. It insists that energy comes in quanta, that uncertainty prevents absolute precision. In a black hole, these two frameworks demand answers at the same time, and yet they give incompatible ones. Relativity predicts smooth, continuous collapse, while quantum mechanics says the fabric of space-time should jitter and resist being squeezed to infinity. This tension is a signal that something deeper is missing. Another example comes from the birth of the universe itself. At the Big Bang, everything was compressed into an unimaginably small, dense state. Conditions where both quantum mechanics and relativity must apply, but again, they give conflicting accounts. Relativity cannot handle such extreme density without breaking down, while quantum mechanics cannot ignore gravity when energy levels are so enormous. To understand the origins of the universe or the ultimate fate of black holes, we need a theory that unites the two, a theory of quantum gravity. Physicists have spent decades searching for such a theory. One of the most famous attempts is string theory, which proposes that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. Each vibration corresponds to a different particle, and the framework naturally includes gravity alongside quantum rules. In this view, electrons, quarks, and photons are simply different modes of vibration. String theory is elegant and ambitious, even suggesting extra dimensions beyond the three of space, and one at a time. But despite its beauty, it remains speculative, awaiting experimental confirmation. Another approach is called loop quantum gravity, which takes a different path. Instead of strings, it suggests that space and time themselves are quantized, that the fabric of the universe is woven from tiny loops like a cosmic mesh. Just as energy comes in quanta, so too might space and time, preventing infinities by giving space-time a smallest possible unit. In this picture, the universe is granular, with the smooth curves of relativity emerging only when seen from far away, much like a picture looks smooth from a distance but reveals pixels up close. These attempt to remind us of something important. Our current theories, powerful as they are not the final word. They are stepping stones, approximations that work brilliantly in certain domains but falter at the edges. The quest for quantum gravity is not just a technical puzzle. It is a search for a deeper understanding of a universe's foundations. It asks whether the cosmos is continuous or discrete, whether time itself is fundamental or emergent, whether space is a stage or a participant in the drama of existence. This search also forces us to rethink some of the deepest questions we can ask. For instance, what is the nature of time? In relativity, time is flexible, affected by motion and gravity, yet still flowing smoothly. In quantum mechanics, time appears as an external parameter, ticking steadily while particles shift probabilities. But in a unified theory, time itself may not exist as we know it. It may be an emergent property, arising from deeper, timeless laws. This possibility unsettles our everyday intuition, but also opens breathtaking vistas. If time is not fundamental, what does it mean for the universe to have a beginning or an end? What does it mean for us, beings who live by clocks and memories? Equally fascinating is the question of space. Relativity shows that space can bend and stretch, while quantum mechanics reveals that particles can be entangled across vast distances, ignoring spatial separation. A theory of quantum gravity may reveal that space is not fundamental either, that it emerges from quantum relationships, from information shared between particles. In this sense, the universe could be less like a stage and more like a web, woven from interactions and correlations. We may find that space is not where the universe happens, but something generated by the universe itself. The challenge of uniting quantum mechanics and relativity is daunting, but is also inspiring. It reminds us that science is a journey, not a finished map. We stand at the edge of knowledge, holding two powerful lights that illuminate different realms but leave the deepest shadows unresolved. And yet, even in their incompleteness, these theories guide us towards something larger, something profound. They suggest that the universe is stranger and more wondrous than either framework alone can capture. As we move forward, it is worth pausing to notice how quantum physics has shifted from a theory of electrons and photons to a key player in the biggest questions of cosmology. It no longer lives only in laboratories or equations, but in the heart of stars, the collapse of galaxies, the birth of the universe itself. The very fact that quantum mechanics touches both the smallest and the largest scales hints that its principles are woven into the deepest fabric of reality. We will take this exploration even further. We'll step into the mysterious world of quantum fields, the stage on which particles themselves appear and disappear. Here, the story of quantum physics expands beyond particles and waves into a universe where the vacuum itself seethes with energy, where empty space is never truly empty, and where the lines between nothingness and something blur. It is a world that challenges not only our science, but our imagination. So far, our journey has been guided by particles and waves, uncertainty and entanglement, and the search for unity with gravity. But to truly understand a quantum universe, we must go deeper, beyond the idea of particles as tiny objects and beyond waves as ripples of probability. At the heart of modern physics lies a framework called quantum field theory, and it changes everything. It tells us that particles are not fundamental at all. Instead, they are excitations of invisible fields that fill the entire universe. To grasp this is to step into one of the most profound insights science has ever uncovered. The universe is made of fields, and particles are their fleeting ripples. Let's start with an everyday analogy. Imagine the surface of a calm lake. At rest, it looks still and featureless. But drop a stone and ripples spread outwards. These ripples are not separate from the water. They are patterns within it. Now imagine that instead of water, the universe itself is permeated by invisible fields. When energy disturbs these fields, ripples form, and those ripples appear to us as particles. An electron is not a tiny billiard ball. It is a ripple in the electron field. A photon is not a little bead of light. It is a ripple in the electromagnetic field. Everything we call matter and energy emerges from these hidden oceans that underlie reality. This idea may sound abstract, but it is the most accurate description of nature we currently possess. Quantum field theory, or QFD, unites the quantum rules we've learned with the principle of special relativity. It explains why particles can pop in and out of existence, why forces arise, and why matter is stable. In QFT, the universe is not a collection of objects bouncing around, but a restless stage of interacting fields. Even the vacuum of empty space is not truly empty, but alive with fluctuations, constantly bubbling with virtual particles that appear and vanish in a heartbeat. What we call nothing is, in truth, a seething sea of possibility. One of the most striking consequences of this framework is that particles are no longer the ultimate building blocks. They are temporary, like waves cresting on the ocean before fading back into the deep. Fields are fundamental. Particles are their visible signatures. This shift in perspective reshapes our understanding of reality. Instead of asking what particles are made of, we ask, what field exists and how do they interact? The answers form what physicists call the standard model of particle physics, a grand catalog of fields and their particles, covering electrons, quarks, neutrinos, and more, along with the forces that govern them. The standard model is astonishingly successful. It has predicted particles and interactions long before experiments confirmed them. For instance, the Higgs boson, sometimes called the God particle, though scientists dislike that nickname, was predicted by QFD decades before it was observed at a Large Hadron Collider in 2012. The Higgs field gives mass to particles, allowing the universe to have structure rather than being filled with weightless light. Without it, there would be no atoms, no chemistry, no stars, no life. The discovery of the Higgs boson was not just a confirmation of a theory. It was the unveiling of a hidden layer of reality. Yet quantum fields also raise unsettling questions. If empty space is filled with fluctuating energy, why does the universe not collapse under its own vacuum energy? This puzzle, known as the cosmological constant problem, remains unsolved. Similarly, while the standard model explains much, it does not include gravity, nor does it account for mysterious substances like dark matter and dark energy that dominate the cosmos. Quantum field theory is powerful, but incomplete. It is a window, not the final view. The concept of fields also forces us to rethink nothingness. We often imagine nothing as an absolute void, the absence of everything. But in the quantum picture, nothing is unstable. Particles constantly flicker in and out of existence, borrowing energy from the vacuum and returning it before the cosmic ledger notices. This activity may seem imaginary, but it has real consequences. For instance, the Casimir effect demonstrates that two uncharged metal plates placed close together in a vacuum feel a tiny force pulling them together. This force arises from quantum fluctuations of the vacuum itself. Even emptiness is alive. At cosmic scales, these fluctuations may have seeded the structure of the universe. According to theories of cosmic inflation, tiny quantum jitters in the early universe were stretched by rapid expansion, becoming the seeds of galaxies and stars. In other words, the grand tapestry of the cosmos may have begun as ripples in the vacuum. From the smallest scales to the largest, quantum fields shape reality. But perhaps the most unsettling aspect of QFD is that it blurs the boundary between something and nothing. Particles can be created from fields if enough energy is supplied, as in high-energy collisions. They can also annihilate back into pure energy, disappearing into the field that birthed them. Matter and energy become interchangeable not just in Einstein's famous equation, but in the dynamic play of fields that constantly swap, interact, and transform. In this view, reality is not built from enduring bricks, but from fleeting patterns in an invisible medium. This vision is both humbling and exhilarating. It tells us that what we see, the solidness of objects, the permanence of matter, is an illusion born of stability in the underlying fields. When we touch a table, we are not touching atoms in the sense of tiny marbles. We are encountering the electromagnetic field that resists our hand. When we see light, we are not seeing little particles flying, but disturbances in a field that carries energy across space. The entire sensory world is a surface of deeper layers, ripples of hidden oceans we cannot see directly. And yet, for all its abstraction, quantum field theory has practical power. It underlies the design of particle accelerators, the creation of new materials, and the functioning of modern electronics. Without it, our understanding of semiconductors, superconductors, and even nuclear reactions would be incomplete. It is both the most theoretical and the most applied of sciences, bridging imagination and engineering. Still, questions remain. If fields are fundamental, where do they come from? Why these fields and not others? Why do they have the strengths and values they do? These mysteries point to gaps in our understanding, hints that a deeper framework still awaits discovery. Just as quantum mechanics once replaced classical physics, so too may another revolution lie ahead, one that explains the origin of fields themselves. As we move onward, we will follow the path from quantum fields to the cosmos itself. We will explore how these ideas connect with black holes, dark matter, and the fate of the universe. We will see how quantum physics reaches from the tiniest ripples of emptiness to the structure of galaxies, binding the story of the small and the vast into one unfolding narrative. The quantum is no longer just a theory of atoms. It is the story of reality itself. By now, we have followed quantum physics from its early puzzles to its astonishing technologies, from its strange interpretations to its hidden fields. We have seen how particles are not little marbles, but ripples in invisible oceans, how the vacuum itself is alive, and how uncertainty and entanglement challenge our notions of reality. But quantum mechanics does not only describe the small. Increasingly, it is tied to the very largest questions: the birth of the universe, the fate of black holes, and the unseen matter and energy that shape the cosmos. To explore these mysteries is to see quantum physics not just as a laboratory science, but as a key to the grand story of existence. Let's begin with black holes, perhaps the most extreme laboratories for testing the laws of physics. As we've seen, they are regions of space-time where gravity is so intense that nothing, not even light, can escape. According to relativity, a black hole forms when matter collapses to infinite density at a singularity. But quantum physics cannot accept this infinite compression. It insists that uncertainty, quantization, and the jitter fields must intervene. What, then, really happens inside a black hole? One of the most surprising answers came from Stephen Hawking in the 1970s. Using quantum field theory near the horizon of a black hole, he showed that black holes are not completely black. Instead, they emit a faint radiation, now called Hawking radiation. This arises from quantum fluctuations in the vacuum near the event horizon, where particle-antiparticle pairs can appear. Normally, such pairs annihilate quickly, returning to nothing. But near a black hole, one particle may fall in while the other escapes, creating the appearance of radiation. Over immense timescales, this process allows a black hole to lose energy and eventually evaporate. The discovery stunned physicists. It revealed that black holes are not eternal prisons, but quantum objects with lifespans and thermodynamic properties. Yet Hawking's insight also created a puzzle known as the information paradox. If matter and information fall into a black hole, and the black hole eventually evaporates into featureless radiation, is the information lost forever? Quantum mechanics insists that information is preserved, never destroyed. But black holes seem to erase it. Resolving this paradox has become one of the central challenges of modern physics. Some believe that information is somehow encoded in the radiation itself, scrambled but not destroyed. Others suggest that the very nature of space-time must be rethought. Either way, the paradox shows that quantum mechanics and gravity are deeply entangled, and that black holes are windows into a deeper theory. Beyond black holes lies another cosmic mystery: dark matter. Astronomers have long noticed that galaxies rotate too quickly for their visible stars to hold them together. Something unseen must provide extra gravity, binding galaxies in clusters. This invisible substance, called dark matter, outweighs ordinary matter by about 5 to 1. Yet despite decades of searching, no one has detected dark matter directly. What is it made of? Here, quantum physics enters again. Many theories propose new particles, weakly interacting, massive, and stable, that can make up dark matter. These particles would be invisible to light, but detectable through their gravitational influence. Experiments deep underground and in space are searching for them, guided by quantum predictions. If discovered, dark matter would extend the quantum story beyond the standard model, revealing new fields and forces. And then there is dark energy, a mystery even greater. In the late 1990s, astronomers found that the universe is not just expanding but accelerating in its expansion. Some unknown energy seems to permeate space, pushing galaxies apart. This dark energy makes up nearly 70% of the cosmos, dwarfing both dark matter and ordinary matter. Its nature is utterly unclear. It may be related to the quantum energy of the vacuum itself, though calculations of vacuum energy produce numbers that are wildly larger than observations. This gap between theory and reality is one of the most glaring problems in physics. If solved, it could reshape our understanding of both quantum fields and cosmology. What unites these mysteries, black holes, dark matter, dark energy, is that they all sit at the edge of quantum theory. They are places where the quantum rules we know are stretched to their limits, demanding new ideas. They remind us that quantum mechanics is not a finished chapter, but an unfinished manuscript, still being written by experiments, observations, and daring imagination. Consider again the origin of a universe. According to the Big Bang Theory, the cosmos began as a hot, dense state that expanded and cooled into the stars and galaxies we see today. But what set the expansion in motion? How did the first structures emerge? Quantum physics offers clues. Tiny fluctuations in the early universe, perhaps arising from quantum uncertainty itself, may have been magnified by a brief period of rapid inflation. These fluctuations became the seeds of cosmic structure, growing into galaxies under gravity's pull. If true, then every star, every planet, every living being traces its roots back to quantum jitters in the first moments of time. The universe itself may be, in a sense, a quantum creation. This perspective reshapes our place in the cosmos. We are not separate from quantum reality, observing it from a distance. We are products of it, born from fluctuations, bound by entanglement, shaped by fields. The same rules that govern electrons and atoms also govern the birth of galaxies. The quantum is not a corner of reality. It is its foundation. And yet, for all we have uncovered, we are left with profound questions. What happens at the heart of a black hole? What is the true nature of dark matter and dark energy? How does quantum physics unite with gravity? What is the fate of information in the universe? These questions are not technical curiosities. They are doorways to deeper truths. They challenge us to rethink what reality is, where it came from, and where it is going. Now, we will step back from the vastness of the cosmos to look at the intimate link between quantum physics and information. We will explore how reality itself may be written in bits of quantum information, how entanglement weaves a fabric of space, and how quantum computers may not just calculate, but reveal truths about the universe itself. If the cosmos is a book, then quantum information may be its language. So far, we have seen quantum physics illuminate both the tiniest and the grandest scales. It explains why atoms are stable, why stars shine, and perhaps even why the cosmos has structure at all. We've looked at black holes, dark matter, and dark energy, with the quantum rules stretched to their limits. But now, let us turn to another revolution born from quantum mechanics, the realization that reality itself may be understood in terms of information. This is not just a metaphor. Increasingly, physicists see the universe not as a collection of things, but as a network of information woven together by the strange logic of the quantum world. To appreciate this shift, we should first recall what information means in the ordinary sense. In classical terms, information is carried by bits, zeros, and ones. A bit is a simple yes or no, on or off, true or false. With enough bits, we can represent anything: numbers, words, images, sounds. Computers process these bits to perform calculations, store memories, and send messages. But at its core, classical information is definite. A bit is either 0 or 1, never both. It lives in certainty. Quantum information changes this. Here, the basic unit is the qubit, a quantum bit. Unlike a classical bit, a qubit can exist in superposition, being both 0 and 1 at the same time, weighted by probabilities. When measured, it collapses into one definite value. But before measurement, it embodies both. This single difference creates astonishing possibilities. While classical computers explore one possibility at a time, quantum systems can explore many simultaneously. It is as though reality itself allows shortcuts through complexity. The power of qubits becomes even greater when we introduce entanglement. Two entangled qubits share a connection so deep that their states cannot be described independently. Measure one, and you immediately know the state of the other, no matter how far apart they are. Entanglement allows quantum information to spread, correlate, and weave together in ways impossible for classical bits. It is not just a resource for computation. It is a fundamental feature of reality. But here's where things become profound. Physicists have realized that entanglement may not just be a tool for building quantum computers. It may be the glue that holds space-time together. Some researchers propose that the geometry of space itself emerges from patterns of quantum entanglement. In this view, distance, dimension, and even gravity arise from the fabric of information. The universe is not built from matter alone, but from relationships, from the way qubits connect. Space, time, and energy may all be emergent properties of quantum information. This idea gained support from the study of black holes. Remember the information paradox, the puzzle of whether information is lost when black holes evaporate. Increasingly, evidence suggests that information is preserved, encoded somehow in an entanglement of particles near the horizon. Black holes, in fact, seem to be ultimate storage devices, with a capacity proportional not to their volume but to the area of their surface. This insight led to the holographic principle, which suggests that the content or region of space can be fully described by information written on its boundary. The universe, then, may be like a hologram, a three-dimensional reality encoded on a two-dimensional surface. Information is not just a way of describing reality. It may be its foundation. At first glance, these ideas sound fantastical, as though they belong more to philosophy than to physics. But they are grounded in mathematics and supported by evidence. Quantum error correction, for example, a tool used in building quantum computers, has surprising links to the way space-time may stabilize itself. What we learn in the lab about controlling fragile qubits might also teach us why the cosmos is robust. The language of information is uniting fields once thought separate: quantum mechanics, thermodynamics, gravity, and computation. The practical side of quantum information is equally revolutionary. Quantum computers, though still in their infancy, promise to solve problems that classical computers cannot. They could simulate molecules with perfect accuracy, unlocking new medicines and materials. They could crack cryptographic codes, forcing us to rethink digital security. They could optimize systems far too complex for classical algorithms, from traffic flows to financial markets. But perhaps more importantly, they are laboratories for exploring quantum reality itself. Each qubit, each entangled pair, is a window into the strange logic of the universe. Beyond computing, quantum information has sparked advances in quantum communication. Because entanglement links particles across distance, it allows for secure communication channels where any attempt at eavesdropping is immediately detectable. Networks of entangled particles, quantum internets, are being developed, promising unbreakable security and new modes of connection. Once again, what began as a philosophical puzzle about measurement has become a tool with world-changing potential. And yet, the most striking part of the story is not the technology, but the perspective it brings. If reality is fundamentally informational, then matter, energy, space, and time are not the ultimate ingredients, but the visible effects of deeper patterns. We, too, as conscious beings, may be part of this informational fabric. Our thoughts, memories, and identities emerge in the processing of information in the brain, which itself is governed by quantum rules. Consciousness, information, and reality may be three aspects of the same underlying truth. This is not to suggest that quantum physics has solved the mystery of consciousness. It has not, but it invites us to think differently about our place in the cosmos. We are not passive observers of a clockwork universe. We are participants in a web of information, woven from entanglement, shaped by uncertainty and alive with possibilities. Every measurement, every observation, is not just a passive recording, but an active moment in the story of reality. As we reflect on this, it becomes clear that quantum physics is more than a branch of science. It is a new language for describing the world, one that blends physics, computation, and philosophy. It asks us to move beyond objects and substances to think in terms of relationships, probabilities, and information. It shows us that what we call reality may be a tapestry of quantum bits, stitched together by entanglement. We will continue this journey by looking not at the abstract world of information, but at the human journey with quantum physics. How this theory has transformed not just science, but culture, art, and philosophy. We will see how the strangeness of the quantum has inspired new ways of thinking, and how, slowly but surely, it has changed our vision of ourselves and our universe. We have followed quantum physics through its mathematical puzzles, its experimental triumphs, and its cosmic implications. We've seen it give birth to technologies like quantum computers and illuminate mysteries like black holes and dark energy. But quantum physics is not just a scientific revolution. It is also a cultural one. Its strangeness, its refusal to fit our everyday logic, has influenced philosophy, art, and even the way we think about ourselves. In this part of our journey, let us step back from equations and experiments and look at the human story of how quantum mechanics has reshaped our worldview. From the very beginning, quantum theory forced scientists to confront the limits of certainty. Classical physics had painted a picture of a predictable universe, where knowledge grew like a steadily expanding circle of light. But quantum mechanics shattered that picture. Suddenly, certainty gave way to probabilities, and reality itself seemed to depend on observation. This was not just a shift in equations. It was a shift in worldview. It forced us to accept that ambiguity is fundamental, not just a matter of ignorance. The world is not merely hidden from us until we discover it. In some sense, it is incomplete until interaction gives it form. This notion quickly spilled beyond science into philosophy. Thinkers began to ask, if reality is probabilistic, what does that mean for concepts like truth, knowledge, and free will? Does the indeterminacy of quantum events leave space for freedom in a universe once thought deterministic? Or does it merely replace one kind of necessity with another, statistical kind? Philosophers wrestle with these questions, seeing in quantum mechanics both a challenge and an opportunity. It undermined the rigid determinism of 19th century materialism, but also raised questions about the role of the observer in shaping reality. The impact spread into literature and art as well. Writers, fascinated by the idea of parallel possibilities, drew inspiration from quantum superposition and the many worlds interpretation. Stories of branching timelines, alternate realities, and characters caught between possibilities found fertile ground. Playwrights and novelists use quantum ideas as metaphors for human choice, ambiguity, and fate. In visual art, the strange beauty of quantum patterns inspired new forms of abstraction, echoing the probabilistic nature of reality itself. Even in music, composers experimented with indeterminacy, leaving parts of their works open to chance, reflecting the spirit of quantum uncertainty. But perhaps the most profound cultural influence of quantum mechanics has been its effect on how we see ourselves. For centuries, humanity imagined itself as living in a clockwork universe, small cogs in a grand machine. Quantum physics replaced that machine with something more fluid, more mysterious, and more participatory. We are not just passive bystanders. Our observations play a role in shaping the phenomena we witness. This is not to say that consciousness creates reality in some simplistic sense, but it does mean that the act of measurement, the act of engaging with the world, is fundamental. We are woven into the process, not floating above it. This participatory role has led some to draw connections between quantum physics and spiritual traditions. Mystics across cultures have long spoken of a world that is interconnected, where separation is an illusion and wholeness is fundamental. Quantum entanglement, with its eerie connections across space, resonates with these ancient intuitions. Of course, science and spirituality operate with different methods and goals, but the parallels have inspired many to see in quantum physics a bridge between material and transcendent ways of knowing. Whether or not these parallels are literal, they reflect a shared recognition that reality is deeper and stranger than appearances. Yet this cultural embrace has also brought misunderstandings. Quantum physics is subtle in its terms, uncertainty, superposition, entanglement are often borrowed in loose or misleading ways. Some have used quantum jargon to justify pseudoscience or magical thinking. It is important to distinguish metaphor from fact, to honor the mystery of the quantum world without distorting it. The real beauty of quantum mechanics lies not in being a catch-all for mystery, but in its precise and disciplined strangeness. It teaches us that truth can be both rigorous and wondrous, that mathematics can reveal worlds stranger than any fantasy. Despite these distortions, the cultural influence of quantum theory has been immense. It has taught us new metaphors for life itself. Think of uncertainty. In everyday terms, we often fear it, seeking to banish it with control. But quantum physics suggests that uncertainty is not a flaw, but a feature. It is what allows atoms to be stable, matter to exist, and creativity to flourish. Without uncertainty, the universe would be sterile. This transforms how we might see our own uncertainties, not as gaps to be filled, but as spaces of possibility. Similarly, entanglement offers a metaphor for human connection. Just as particles remain linked across vast distances, so too our lives are bound together in ways not always visible. What we do ripples outward, touching others in unexpected ways. Again, this is not a scientific claim, but a poetic one. Yet it shows how quantum ideas, properly understood, can enrich not just our technology, but our imagination. Even the idea of superposition has entered culture as a symbol for possibility. Before measurement, a particle exists in many states at once. Likewise, before choices are made, our lives hold many potential futures. This does not mean we literally live in superposition, but the metaphor resonates. The future is not fixed, and possibility is as real as actuality. In this way, quantum physics has become a language for grappling with human experience. At its heart, the cultural impact of quantum mechanics is about humility and wonder. It reminds us that the world is stranger than we thought, that our intuitions are not the final measure of truth, and that mystery is not a gap in knowledge but a doorway to deeper understanding. Science does not reduce the world to dull machinery. It expands our sense of what is possible. Quantum physics is proof that reality is far richer, subtler, and more astonishing than common sense alone could imagine. We have walked through the origins of quantum theory, traced its strangeness, followed its role in technology, and even seen its impact on culture. Yet the most exciting part of the story may be what lies ahead. Quantum mechanics, for all its triumphs, is not a finished theory. It works astonishingly well, but it leaves deep questions unanswered. To glimpse the future of physics, we must ask, what comes after quantum mechanics? What new revolutions await? And how might they transform both our understanding of reality and the shape of human knowledge? Let us begin with the most pressing challenge, the union of quantum mechanics and gravity. Today, physics has two great pillars. On one side stands quantum mechanics, describing particles, atoms, and fields with extraordinary precision. On the other side stands general relativity, Einstein's theory of gravity, explaining the structure of space-time, black holes, and the expansion of the universe. Each is brilliant, but they do not fit together. Where quantum rules should apply to space-time itself, contradictions appear. Black holes, the Big Bang, and the very fabric of the cosmos are arenas where both theories must act, yet neither can fully rule. The search for a deeper framework, one that unites quantum mechanics and gravity, is perhaps the greatest quest of modern physics. One candidate is string theory, which suggests that the fundamental units of reality are not particles, but tiny vibrating strings. Different vibrations correspond to different particles, like notes on an instrument. String theory naturally incorporates gravity and quantum mechanics, and it even predicts additional dimensions beyond the familiar three of space and one of time. But it is mathematically complex and difficult to test. Critics argue that without experimental evidence, string theory remains more of a possibility than a discovery. Still, it offers a glimpse of how a deeper theory might look, one where the diversity of particles emerges from simple, elegant vibrations. Another path is loop quantum gravity, which takes a different approach. Instead of smoothing space-time into strings, it suggests that space itself is quantized, built from tiny loops of energy. Just as matter comes in quanta, so might space and time. In this picture, the smooth continuum of space-time is an illusion. like a digital image that appears continuous but is made of pixels. At the Planck scale, the smallest scale imaginable, space-time might be a weave of quantum threads. If true, this could resolve the infinities that plagued black holes in the Big Bang, providing a quantum foundation for gravity itself. Beyond these specific theories, there's a tantalizing possibility that information is the true foundation. As we saw earlier, entanglement may weave space-time itself. Some physicists propose that by focusing not on particles or strings, but on quantum information, we may arrive at a theory that unites all forces. This would not just be a new physics, but a new philosophy. Reality is a web of information with matter, energy, and geometry as emergent properties. In this vision, the universe is less like a machine and more like a computation, endlessly unfolding its patterns. But the future of quantum physics is not only about cosmic theory, it is also about technology. Quantum computers are in their infancy, fragile and limited, but progress is rapid. In the decades to come, they may achieve quantum supremacy over classical computers in a wide range of tasks. This could revolutionize fields from medicine to materials science. Imagine designing new drugs by simulating molecules exactly, or creating new energy sources by understanding reactions at the quantum level. Imagine solving problems of optimization, how to allocate resources, manage traffic, or plan global logistics, with an efficiency that classical computers cannot approach. These are not fantasies, but real possibilities, grounded in the strange power of superposition and entanglement. Quantum communication, too, will grow. Networks of entangled particles, quantum internets, are already being tested. Such systems could provide unbreakable security, as any attempt to intercept the communication would disturb the entanglement and be noticed. They could also allow new forms of distributed computing, where quantum resources are shared across the globe. In time, quantum networks may be as transformative as classical ones, reshaping how we connect, share, and collaborate. Yet with power comes challenge. Quantum technology will raise questions of ethics, security, and control. Who will own the quantum computers of the future? How will quantum cryptography reshape geopolitics? What new inequalities or risks may arise? As with all technologies, the quantum revolution will not only expand possibilities, but test our wisdom in using them. The future also holds mysteries in the foundations of quantum mechanics itself. After more than a century, we still debate what the theory really means. Is reality split into many worlds, branching at every measurement? Does collapse occur when consciousness is involved? Are hidden variables at work, deeper than we know? Or is the entire debate misguided, with quantum mechanics simply being the best description possible? No interpretation required? These questions remain unsettled. Perhaps future experiments will test the limits of quantum theory, revealing cracks where a deeper truth shines through. Already, researchers are designing experiments to push the boundaries of superposition and entanglement, involving larger and larger systems. Who knows? One day we may see quantum effects in living organisms, or even in the brain, challenging our ideas about life and mind. The future of quantum physics is thus not a single path, but a landscape of possibilities. At its heart lies a paradox. Quantum mechanics is the most successful theory in science, yet it is also incomplete. It works perfectly, yet it points beyond itself. This tension is not a flaw, but a source of creativity. It drives physicists to imagine, to experiment, to reach for new ways of seeing the world. For us, as explorers of these ideas, the lesson is clear. The story of quantum physics is far from over. We live in a time when its next chapters are being written, not only in laboratories and equations, but in culture, technology, and imagination. The mysteries ahead are as profound as those that launched the quantum revolution a century ago. To follow them is to participate in one of the greatest adventures of human thought. We have traveled far into landscapes of quantum theory. Atoms, particles, fields, entanglement, black holes, information, and even the future physics. The concepts are vast, the mathematics intricate, and the implications profound. It is easy to feel overwhelmed, to imagine that this subject is only for experts in ivory towers, speaking in equations that seem like another language. But quantum physics at its heart is not about intimidating formulas. It is about patterns in nature, revealed slowly and carefully. It is about curiosity, patience, and a willingness to think differently. In this part of our journey, let us pause and talk about what it means to understand quantum physics slowly. The first step is to release the urge for instant clarity. In many areas of life, we are trained to seek quick answers, clear solutions, and tidy explanations. But quantum mechanics resists such simplicity. It is not that it is impossible to understand. It is that understanding must come gradually, in layers. Imagine climbing a mountain. From the base, the peak looks unreachable. But step by step, with pauses for rest and reflection, the view changes. Each stage reveals more. Quantum physics is like that. The climb is worth it, but it cannot be rushed. The second step is to cultivate intuition. Mathematics is a precise language of physics, but intuition is the bridge between math and meaning. To build it, we must lean on analogies, stories, and images. For example, think of superposition not as an abstract wave function, but as a coin spinning in the air, neither heads nor tails until it lands. Think of entanglement as two dancers moving in perfect sync, even if they are on different stages. These analogies are not perfect, but they are stepping stones, helping us grasp concepts that are otherwise invisible. Slowly, as we move from analogy to mathematics, intuition deepens and the fog begins to lift. Another key is to embrace uncertainty. This is perhaps the hardest lesson, because we often equate understanding with certainty. But in quantum mechanics, uncertainty is not ignorance. It is reality itself. Accepting this does not mean giving up clarity. It means shifting our sense of clarity to include probability, possibility, and openness. Instead of asking, what is a particle doing exactly, we learn to ask, what are the chances and what do they mean? This shift in perspective takes time. But once it is made, quantum mechanics feels less like a contradiction and more like a new kind of logic. Alongside patience and intuition, there is also the need for playfulness. Quantum physics, for all its seriousness, invites us to play with ideas. Thought experiments, like Schrodinger's cat or Einstein's photon boxes, were born not from rigid calculation, but from imaginative play. To learn quantum mechanics is to engage in this play, to ask what-if questions, to picture impossible scenarios, to explore without fear of being wrong. Often, the best insights come when curiosity is allowed to wander freely without the pressure of immediate answers. But we must also remember that quantum physics is not only abstract, it touches the everyday world in surprising ways. The light from your phone screen, the GPS guiding your travels, the chips inside your computer, all depend on quantum principles. By connecting the theory to technology, by seeing its fingerprints in daily life, the concepts feel less distant. Each time you hold a device, you are holding the fruit of quantum mechanics. To learn slowly is to notice these connections and let them remind you that quantum theory is not just in textbooks, it is in your hands. Another part of learning slowly is to practice returning. Quantum mechanics often resists understanding at first encounter. A concept may seem hopelessly confusing, even after hours of thought. But when you return to it later, after gaining other insights, suddenly it makes sense. This is not failure, but the natural rhythm of deep learning. Like a spiral, you circle back to the same ideas, each time from a higher vantage point. Slowly, the pieces fit together. Patience here is not optional. It is essential. It also helps to recognize that mystery is part of the beauty. We often think that to understand something is to strip away its mystery, leaving only cold facts. But in quantum physics, mystery and understanding grow together. The more we understand, the more we realize how much remains hidden. This is not discouraging but inspiring. It means that quantum mechanics is not a puzzle with final solution, but a doorway into endless discovery. To learn it slowly is to savor this balance of knowledge and wonder. At a deeper level, learning quantum physics slowly is about changing how we think. It invites us to loosen our grip on rigid categories, to be comfortable with paradox, and to imagine reality in new ways. These are not just scientific skills, but human ones. They help us face uncertainty in life, adapt to complexity, and see connections where before we saw only separations. In this sense, The slow study of quantum mechanics is a kind of mental training, a practice in flexibility and openness. And here's the most important point. You do not need to master quantum mechanics to gain from it. You do not need to solve equations or become an expert. Simply by engaging with the ideas, slowly, patiently, with curiosity, you participate in one of humanity's greatest adventures of thought. The journey itself is a gift. Each step brings not only new knowledge, but a new way of seeing the world. So when we say quantum physics explained slowly, we mean more than a method. We mean a philosophy. That deep understanding takes time. That mystery is not an obstacle but an invitation, and that patience is the key to insight. By walking slowly, we go farther. By pausing, we see more. By allowing ourselves to wonder, we find joy in discovery. We have taken our time with quantum physics, moving slowly, carefully, letting each concept settle before climbing higher. Along the way, we have discovered strange new worlds. Particles are waves, uncertainties are fundamental, entanglements that defy distance, and a cosmos that may be woven from information itself. We have seen technology transform, culture shift, and imagination expand. And we have paused to consider how to learn slowly, with patience and wonder. Now, as our journey nears its end, it is time to step back and ask, what does it all mean? What has quantum physics truly taught us about reality and about ourselves? The first lesson is that reality is deeper than appearances. Our everyday experience suggests a solid, predictable world of objects with definite positions and clear behaviors. But beneath that surface lies a realm where certainty dissolves and possibility reigns. Particles do not have fixed properties until they are measured. Energy comes in discrete quanta. Space and time themselves may be emergent, born from networks of information. This is not a rejection of reality, but an expansion of it. The world is more subtle, more layered, more astonishing than common sense alone can capture. To live with this knowledge is to carry a kind of humility. The awareness that our perceptions are not the final word, but only a surface glimpse of something richer. The second lesson is that uncertainty is not weakness, but strength. Classical physics promised certainty, but quantum mechanics gave us probabilities. At first, this seemed like a loss. How could science be trusted if it could not predict exact outcomes? But slowly, we have learned that uncertainty is not ignorance. It is the structure of reality itself. Without uncertainty, atoms would collapse, chemistry would fail, and life would be impossible. Uncertainty is the engine of possibility, the source of creativity in nature. It teaches us that unpredictability can be fertile, and that limits can also be gifts. The third lesson is the power of connection. Entanglement, once dismissed as spooky action, has proven to be not only real but fundamental. It shows us that parts of the universe cannot always be understood in isolation. They are linked in ways that defy separation. The universe is not merely a collection of objects, but a web of relationships. This insight resonates beyond physics. In our own lives, too, connection is fundamental. We are not isolated beings, but entangled participants in a shared reality. Quantum mechanics reminds us that wholeness, not fragmentation, is the deeper truth. The fourth lesson is that information is reality's hidden language. Qubits, holograms, and black holes have all pointed us toward a vision where information is a foundation. Matter, energy, and even space-time may emerge from informational patterns. If so, then the universe is less like a machine and more like a story, dynamic, unfolding, endlessly expressive. To understand reality is to understand the way information is structured, shared, and transformed. This changes not only science but our philosophy, inviting us to see ourselves as participants in a grand informational dance. The fifth lesson is about wonder. Quantum physics has shown us that science is not the conquest of mystery, but its deepening. Each answer opens new questions. Each discovery reveals new puzzles. Far from banishing wonder, physics multiplies it. The quantum world is not merely useful or practical. It is beautiful, mysterious, and awe-inspiring. To encounter it is to stand in a cathedral of nature, filled with patterns stranger than any dream. Slowly, as we let the strangeness in, wonder becomes not a fleeting feeling, but a way of seeing. But perhaps the deepest lesson is about ourselves. In grappling with quantum mechanics, we are reminded of the limits of human knowledge and the courage it takes to step beyond them. The pioneers of quantum physics did not find the answers easy. They struggled, debated, and doubted. Yet by moving slowly, by questioning assumptions, by daring to imagine the impossible, they reshaped our world. Their story is also our story. To learn quantum physics, even as amateurs, is a share in that spirit of curiosity, humility, and persistence. It is to join a tradition of seekers who refuse to stop at the obvious, who are willing to embrace confusion as the beginning of wisdom. As we near the end of this journey, it is worth remembering that quantum physics is not a distant domain. It is the reason stars shine, the reason matter holds together, the reason technology works. It is woven into our bodies, our tools, and our universe. To study it slowly is to draw closer to the fabric of existence itself. And in doing so, we discover that science is not just about knowledge, it is about meaning. It tells us not only how the world works, but also how we might live within it. With humility, with curiosity, and with wonder. As we step further into reflection, it becomes clear that our journey through quantum physics has been less like reading a textbook and more like following a long and winding story. At times it felt like a detective tale, with strange clues that made no sense until later chapters. At other times, it was a philosophical dialogue, raising questions about knowledge, perception, and reality. And all along, it has been a journey of wonder, one that asks us to slow down, listen, and allow the world to reveal itself in its own language. To make sense of it all, let's imagine our story as a great arc. At the beginning of the arc, we stood in a world of certainty, the world of classical physics. Here, the rules seemed clear and comforting. Objects had definite positions, causes led predictable effects, and the universe appeared like a clock, ticking forward with precise inevitability. It was a world where knowledge promised control, and mystery seemed destined to fade away. Then, as our story advanced, cracks appeared in that certainty. Experiments revealed shadows that did not fit the classical mold. Light behaving like both particle and wave, electrons refusing to settle into clear orbits, black-body radiation, exposing limits to the old equations. The neat picture began to blur. This was the rising tension of our story, the point where familiar began to give way to the strange. Slowly, as if turning a page, we entered the quantum world. Here, the characters changed. Particles became probabilities, waves became superpositions, and certainty gave way to chance. The story became surreal, filled with paradoxes and riddles. A cat could be both alive and dead. A particle could be in two places at once, and distant twins could mirror each other's fate across the void. It was a world that defied intuition but demanded respect, for the experiment spoke with clarity even when our understanding faltered. As the story deepened, we learned to let go of the demand for simplicity. Instead, we began to see the quantum world as layered, like a great tapestry. Entanglement showed us threads of connection that ignored distance. The uncertainty principle showed us patterns of limits that sustained existence itself. Quantum tunneling revealed the hidden passages through which nature moves. Each discovery added a layer, and slowly, a new picture emerged. A universe not of isolated things but of relationships, not of fixed certainties but of dynamic possibilities. The middle of our story was rich with consequences. Quantum physics was not just an abstract idea, but a force that reshaped the world. Out of its strangeness came lasers, computers, semiconductors, and medical imaging. Out of its riddles came quantum computing, quantum cryptography, and new visions of the cosmos. Here, the story showed us that even the most puzzling truths could bear fruit, that the abstract could transform the concrete, and that patience with confusion could lead to revolutions in clarity. But as with all great stories, the most important parts were not just about technology or discovery. They were about meaning. Quantum physics asked us to reconsider what we mean by reality. Is the universe deterministic or open? Do things exist independently or only in relation? Is information the foundation of being? And if so, what does that say about us as observers, as participants, as conscious beings? These questions push us beyond science into philosophy, reminding us that knowledge is never separate from the human spirit that seeks it. At this stage of the arc, we began to recognize that our story was also about us. The pioneers of quantum mechanics were not abstract minds. They were human beings grappling with wonder and confusion, much like we are now. Their courage lay not in finding quick answers, but in enduring the uncertainty, in accepting paradox, and in daring to believe that reality could be stranger than any dream. Their story of persistence mirrors our own journey of learning, where progress often means being willing to be uncomfortable for a long time until the pieces begin to fit. And now we find ourselves near the top of the arc, looking back and forward at once. We can see how far we've come, from the familiar certainties of classical physics, through the riddles of the quantum realm, into the age of quantum technology and beyond. We can also see that the story is not finished. New chapters await in the mysteries of quantum gravity, the search for unification, and the exploration of the informational foundations of the cosmos. The arc does not close but bends onward into horizons not yet written. But perhaps the most important insight of this reflection is that the pace of the story matters. If we had rushed, we might have gathered only fragments, technical definitions, strange anecdotes, half-understood paradoxes. By moving slowly, we have allowed each piece to take root, to settle, and to reveal its meaning and context. This is not just a way to learn physics, but a way to live. To let life's mysteries unfold without forcing them, to trust that confusion can lead to clarity, and to value depth over speed. To live in a quantum universe is to live in a reality that is deeper, stranger, and more dynamic than our senses alone can grasp. It means recognizing that beneath the surface of everyday life, where objects seem solid and predictable, there exists a hidden dance of probabilities, uncertainties, and entanglements. And while that dance may seem distant from the ordinary concerns of our days, the truth is that it shapes every aspect of our existence. The very fact that atoms hold together, that light warms us, that matter forms the complexity of life, all of it is quantum through and through. So what does it mean in human terms to inhabit such a world? First, it means we must embrace mystery as part of knowledge. In a classical universe, knowledge seemed to offer the promise of certainty. If you could measure all the forces and positions, you could predict the future exactly. In a quantum universe, certainty dissolves into probabilities. Knowledge does not vanish. It becomes subtler, more layered. We cannot predict the exact moment a particle will decay, but we can map the shape of possibilities with precision. To live in a quantum world is to accept that mystery is not the absence of knowledge, but one of its deepest forms. Mystery is not what remains when science has failed. It is what science itself reveals when it looks closely enough. Second, to live in a quantum universe means to understand the creative power of uncertainty. Every time an electron chooses one path out of many, every time a photon collapses from a spread of possibilities into a single reality, the world is renewed. This is not randomness for its own sake. It is a kind of openness written into the fabric of reality. Without it, stars would never burn, atoms would never form, and life itself would be impossible. For us, this suggests something profound, that unpredictability is not a flaw in life, but its foundation. The unknown future is not simply chaos. It is possibility. Third, it means to see ourselves as part of a connected whole. Entanglement teaches us that the universe cannot always be separated into independent parts. What happens here can be bound to what happens there, across space and time, in ways that defy intuition. While this truth arises from physics, it carries a broader resonance. Human life, too, is not isolated but entangled in relationships, in societies, in ecosystems, in histories. To recognize this is to live with a sense of interconnection, to know that actions ripple outward and that wholeness is as real as individuality. Fourth, living in a quantum universe invites us to appreciate information as a hidden fabric of being. If matter and energy emerge from patterns of information, then reality is less like a machine and more like a great story, unfolding in time. Each qubit, each field, each wave of probability is part of the script by which the cosmos expresses itself. And if we are conscious beings, able to perceive and reflect, then we too are participants in this grand informational flow. Our thoughts, our choices, our words are not outside the universe, but within it, woven into its fabric like threads in a tapestry. Fifth, to live in a quantum world is to cultivate wonder as a way of life. Wonder is not merely a reaction to the unusual. It is a stance of openness to the ordinary as well. Every time light bends in a rainbow, every time an atom holds its bonds, every time a bird navigates by Earth's magnetic field, quantum laws are at work. To see this is to transform daily life into a place of awe. Science does not reduce the world's beauty. It multiplies it. The equations of physics are not barriers to wonder, but invitations to see deeper, to stand in awe of the hidden harmonies that shape existence. But there is also a sixth meaning, one more subtle. To live in a quantum universe is to recognize the limits of our understanding. Quantum mechanics, for all its precision, still leaves unanswered questions. What is the ultimate nature of measurement? Does the wave function describe reality itself, or only our knowledge of it? How does quantum theory join with gravity to describe the whole cosmos? These questions remain, and perhaps they always will. To accept this is to live not with frustration, but with humility. The universe is vast, and our knowledge is always partial. Yet in that partiality lies the dignity of being seekers, beings who stretch toward truth even when it outruns us. This perspective changes not only how we think, but how we live. If uncertainty is creative, we can face the unknown future with courage rather than fear. If connection is fundamental, we can honor our bonds to one another and to the earth. If mystery is part of knowledge, we can learn to rest in questions without demanding immediate answers. And if wonder is the deepest truth, then life itself becomes a practice of awe, a daily meditation on the strangeness and beauty of being. Quantum physics does not tell us how to live in a moral sense. It does not prescribe values or dictate choices, but it does shape the atmosphere in which we make those choices. It reminds us that life is fragile, contingent, and yet profoundly connected. It teaches us that the world is not a finished product, but an ongoing creation. And it invites us, in our own small ways, to participate in that creation with curiosity, with care, and with reverence. As our journey draws closer to its end, we find that the slow path has given us more than scientific facts. It has given us a way of seeing, a perspective in which uncertainty is beauty, connection is truth, and wonder is wisdom. The final step is to gather all these threads into one closing reflection, a final chapter in which we will not so much conclude as open the door to future journeys. We have walked a long road together, step by step, never rushing, always taking time to let the ideas unfold. From a first spark of curiosity about the quantum world, through its puzzles and paradoxes, into its technologies and philosophies, we have let the story reveal itself slowly. Now, as we stand at the end of this journey, it is time to look back, to gather the threads, and to ask what it all meant. At the beginning, we stood in a world of familiar, a place where physics meant certainty, where the universe was imagined as a great machine ticking forward with precision. It was a comforting picture, but one that began to crack under pressure of new discoveries. Light was not only a wave, but a particle. Atoms did not behave like tiny solar systems, but like probability clouds. The old rules bent and finally broke. This was the first turning point of our story, the moment when the world revealed itself to be stranger than anyone had dared to imagine. Slowly, we entered the quantum realm, a place where paradoxes lived. Here, uncertainty was not a flaw, but a principle. Here, entanglement showed us connections that defied space and time. Here, particles slipped through barriers, waves collapsed into outcomes, and reality itself seemed to flicker between possibility and actuality. These ideas challenged not only science, but imagination itself. To learn them slowly was to reshape the way we think, to loosen our grip on certainty, and to accept that truth is sometimes layered, subtle, and mysterious. As we moved deeper, we saw that quantum physics was not just theory, but transformation. From its equations came lasers, computers, semiconductors, and the very fabric of modern technology. From its principles came quantum computing, quantum cryptography, and the beginnings of a new technological revolution. What began as puzzling abstractions became engines of change, reshaping the world in which we live. Yet the journey was never only about machines. At its heart, it was about meaning. Quantum physics asked us profound questions. What is reality? What is knowledge? How do we live in a world where uncertainty is fundamental? Where connection is deeper than separation? Where information may be the foundation of being itself? These questions carried us beyond science into philosophy, into wonder, into the very way we see ourselves as participants in the cosmos. Along the way, we reflected on the pioneers of quantum mechanics, not as distant figures, but as fellow travelers who, like us, wrestle with confusion, doubt, and awe. Their story reminded us that knowledge is not a straight path, but a winding road, one that demands patience, humility, and courage. They did not conquer mystery. They learned to walk with it. And in doing so, they open a new chapter of human understanding. Now, standing at the end of our slow exploration, we can see the lessons more clearly. We have learned that reality is deeper than appearances, that uncertainty is not weakness but strength, that connection is fundamental, that information is central, and that wonder is not decoration but truth. We have learned that to live in a quantum universe is to live with humility, with openness, with awe. But perhaps the greatest lesson of all is about slowness itself. In a world that rushes, that seeks instant answers and quick solutions, the quantum universe resists. It asks us to pause, to let the strangeness sink in, to sit with questions that may not have immediate answers. In moving slowly, we discovered more than facts. We discovered perspective. And that perspective is something we can carry with us beyond physics into life itself. For life, too, is quantum. It is uncertain, connected, layered with possibilities. It is filled with mysteries that reveal themselves only with patience. And like quantum physics, it rewards those who move slowly enough to see its patterns, to appreciate its beauty, and to live with wonder. So here, at the close of our journey, let us not think of this as an ending. Quantum physics does not conclude. It opens. Every experiment raises new questions. Every discovery reveals new mysteries. The story is not finished, and perhaps it never will be. But that is its gift. It leaves us not with finality, but with invitation. The invitation to keep learning, to keep wondering, to keep walking slowly into the unknown. And so, we close this story the way we began it, with curiosity. The universe is vast, mysterious, and alive with possibility. To explain it slowly is not to tame it, but to honor it, to give it space to speak. And as long as we are willing to listen, patiently, with humility and awe, the universe will continue to whisper its secrets, one quantum at a time.